Thank you very much. So the image and range of an operator I shall denote by image img of the operator T is the map or image of the element of the domain under this operator. That means T domain of T is one. And this is same as if we write in a set theoretic way, TU such that U is in the domain of T. And then you also have another notion which is called kernel, or this is also called null space. So kernel also called null space. I shall denote it by ker of T. So this is the elements in the domain for which the operator gives 0. So U in domain of T such that T of U equals to 0. All right. And both of these are linear subspaces of our Hilbert space. Yeah, so of T, image of T, they are linear subspace of our Hilbert space. Now, you may also encounter this notion before, but let me introduce formally. So we talk about something like restriction of an operator, which we will need, and also then there is the notion of extension of an operator. So by an operator, we mean T from domain of T to some Hilbert space. And now the restriction another definition, restriction of an operator T, which means from domain of T to some Hilbert space H, we mean, so this operator, there are several symbols. Let me use this notation. So when we tell about restriction, we have to tell restriction on where. So a restriction of this operator on a linear subspace, let's call it D. Again, let me use a different D because I want to use that D later. So this is a linear subspace of our Hilbert space. This means that now this is the domain. So now domain is D to H. And how this is functionally defined? So you take as usual element of that and T restricted on D U is defined as 0. Yeah, what it is can be. Okay, so restriction means you are actually shrinking the domain. Yeah, restriction, restrict. Okay. Now you may think, oh, sure, right, right. Thanks. Otherwise, you cannot take restriction. Thanks. Okay, now you consider the other way around. Instead of restrict, you want to extend it. Okay, and that's called extension. So to define extension, first, let me consider another operator. So S is another operator, which means it has its domain. Great. Now, when we say S equals to T, in no, this is in LaTeX up harmon right, or you can just write it. Okay, so maybe I write here. I use this notation. Yeah, you can also use straight, whatever you like. Is it clear now? Mhm. Yeah, it's not clear. Feel free to ask. So when to matrices, can you repeat LaTeX notation? Okay, LaTeX, I think this is called backslash up. Right, if I'm not mistaken. Okay. Okay. So when two matrices are same, then you say, okay, the matrices are same because they have because matrices are defined. Matrices don't have the domain issue, so the same means they are same as operator. But now, since we have a domain issue, they are equal if and only if their domain coincides and for all u in their domain. So you take any of these domain, doesn't matter, because both domain are same. So let me just write S equals to SU equals to TU. Okay, that's I think also expected. Now we go for extension. So we call T T is an extension of S if, okay, so first notation, that means S, sometimes people give this thing, okay, maybe I use different color. Some people use this equals notation, some don't. Okay, so it's like a set theoretic notation, but do not think as a set. This is an operator. Okay. So by extension, we mean that when extension of that when the domain of S is contained in the domain of T, and for all U in domain of S, S of U equals to T of U. Okay, so that's the notion of extension. And I think these are fairly intuitive, that what you actually expect. You can also say that S is a restriction of T. That's also equivalent. So you can also write S is the restriction of T. Okay, same. Okay, so after these terminologies, now let me ask and also recall. So we go back a bit here in our image and kernel. So in linear algebra, when you have kernel and image, there is a very powerful theorem relating these two. Could you recall what was this theorem? Anyone recall about rank nullity theorem? Yeah, exactly. So rank nullity theorem tells that the domain dimension of the domain is equals to dimension of the range plus dimension of kernel. Now, if we go for bounded operators, and remember we have a separable Hilbert space, so that means we have nice orthonormal basis. So there is a slogan, okay, in theoretical physics that operators are like matrices. So if I write heuristically this way, the slogan tells that operators, I mean, I should not write equal, but let's put this way, are same as matrices. So probably some of you have heard this slogan. Now, if we are in a bounded operator, and again, we have Hilbert space, so we can write in a basis, and then for basis, we can have a matrix representation. However, this matrix is infinite dimensional, right? Because your Hilbert space is infinite dimensional, so you will have a matrix which has infinite number of rows and infinite number of columns. But you can still say, okay, I have some sort of matrix. So let's write red. So this is an operator T, which is a bounded operator. We have nice notation now. So this is a bounded operator. And then by choosing some basis, you can cook up yeah, 1, 1, Tij, sort of thing. Matrix. On the other hand, when you have a matrix, it's called M, you also have elements Ij, but in this case, Ij are finite. So maybe I follow the other earlier approach. Again, a matrix 1, 1, but you have something here. You have something here. So let's call it n by n matrix. So first row, and let's put column m, and this is n, sorry, n m, and so on. Yeah. Okay. So you see that although you can view intuitively this as a form of this, there is no problem. But in practice, this is not going to work because you never know what is here, right? On the other hand, here you know. So when we say that we know a matrix, what does it mean? It means that we know all the elements of a matrix. And now if we want to view an operator as a matrix, a bounded operator as a matrix, then this is not true because we do not know all the elements of this matrix representation of this operator, unless there is something very specific case. Yeah. So that's why you can view this for intuitive reason, there is no problem. But in practice, this is not true. And now you are going to see perhaps the first instant why this rigor thinking is important. So as one of our participants wrote, what is this rank nullity theorem, which tells that the dimension of the domain equals to dimension of the image plus dimension of the kernel. Now, question. What is here? So question to all of you, what do we expect here? Do you expect some generalization of this theorem? Or what can be operator version of rank nullity theorem? Or do you expect it same? Okay, so who thinks both are same? Yes, that's precisely any of or all the at least one of these dimensions can be infinite, and that's why you don't have a rank nullity theorem for bounded operators on a Hilbert space. So some of us ask this question like, can we see the difference concretely? Also in the context of quantum mechanics. So we haven't gone into quantum mechanics, but I hope now you can see it's not just only precise way of writing same thing, but you detect something that is not present in this world, but this is true for matrices. So operator equals to matrices is not right. Is it clear to all of you? Okay, thanks. And in fact, there are more. So this is not only one, but as I told, I want to give you some of the main highlights so that you can think and you can learn more if you're interested. So I hope from or by this 3 lecture you have realized that it's not bad to think intuitively, but there are situations when it's not going to work. It's just not going to work, and this is one of these situations. All right. So now let me go to so I think all of you or some of you have seen there was a discussion, like to give an intuitive idea or to relate with quantum mechanics. Yeah, and of course that we are interested. Unfortunately, quantum mechanics require quite sophisticated level of mathematics. So we cannot just tell right now, look, this is important and this is how it relates to quantum mechanics, because we have to develop the machineries. But something we have already done, and this is not in a full-fledged form, but yet we can talk about it. And that's what now I am going to give you. So you all have seen this before. This so-called momentum operator. Sorry, I mean position operator. In quantum mechanics. So we haven't talked anything about quantum mechanics. That's why this is, I am not going to discuss now, but at some point we shall discuss about it. But this operator we are going to discuss, you have already seen. And that's why I want to give you at least first, let's call it impression, how things are that. So definition, sorry. So now we are considering very specific Hilbert space. The reason is we will discuss it later when we are going to discuss quantum mechanics. RD with the canonical measure. So I'm not writing it. Okay. And I equals to 1, 2, dot, 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 D. Now we define domain of some operator xi as the elements of this Hilbert space such that xi product of element of domain, element of a domain is also in the Hilbert space. So you have seen this condition also before, but now we are looking at more systematically. And now how the operator is defined. So this is the multiplication operator defined from domain of xi to h. You take an u and it maps to m xi u equals to xi dot u. And xi is the ith component of the vector x. So maybe I should write somewhere here. X equals to x1 dot 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 xt. This is a vector rt. Okay, so that is called the position operator. So now you have seen this multiplication by xi, I mean, with a general function before, but now we are choosing a specific function, which is basically an element of R. And if we choose a particular one, you can also take any x if you like, but it's the same. So we take a particular coordinate, okay? So now why it's called position, I think this is fairly obvious, because if we think in terms of coordinate, then since it's picking up a position, that is called a position, and this is the multiplication operator corresponding to position, that's why it's called position operator. Why in quantum mechanics, what it has significance, that you have to wait a bit. But now, for the time being, take in a black box. This is some operator that arises in quantum mechanics. Now, as we have discussed earlier, here. So here we discuss multiplication operator by say, reasonable f. And what we have seen, this is bounded if and only if this function is L infinity, right? But now nature tells us, no, not most general function. You have to take this specific function. And this specific function is not L infinity. Therefore, the position operator is not a bounded operator. Now, what it talks about physics or quantum mechanics. So if something is a bounded operator, then we know the domain is the whole Hilbert space. But in this case, since this is not a bounded operator, we cannot take the domain as the whole Hilbert space. In other words, I mean, we will see a very concrete example in quantum mechanics, but if you think about some physical system, and then if you want to visualize this way, by the way, I also want to make this remark. So although we are talking about, so this is true for any dimension d, but in physics, d equals to 3. Why? Because we have 3 spatial dimension. Okay, it's just an experimental fact. There is no fundamental theory which can tell us why we have 3 space dimension. All right. Okay, so now think about in terms of this thing. So say this is our universe, R3. And what is L2R3? This is some space defined everywhere over R3. So this is L2 R3. Now, this say mathematical analysis tells us you cannot define this operator everywhere on R3. Rather, you have to define on some dense subset of R3. So is it clear how this differs from the, say, physical way of thinking? I give you some time to digest, because that's really crucial. What really differs from the intuitive notion and from the proper notion. So if you even do not know quantum mechanics, don't worry. Just take this information that this operator arises naturally, okay? And then this is an obvious conclusion, right? So are there any questions? Any comments, or is it clear like how this viewpoint changes the way we used to view operators, and how bounded and unbounded operator is really a very serious thing to differentiate, otherwise we miss lots of things. Okay, I do not see any questions, so should I go ahead? Probably is everything clear, but please take your time and ask your question. All right. Um, so we have also seen it before, but now we have very concretely seen one of the operator of our interest for now and later is an unbounded operator. And if you remember the way we initiated, and again, those who know, they know, and if you are not familiar, then we will discuss it later. But for the time being, take as a black box. In quantum mechanics, there is some differential equations, the so-called Schrödinger equation, which looks like this. Here. And we want to solve this equation or know about solution of this equation. And we also want to define all the operators, in particular interesting operators in quantum mechanics. Now, before going to most general case, since it's a differential equation, as you can see here, and I hope large number of you are also familiar with heat equation, this is also a differential equation. And so you are familiar with a differential operator, yeah, right, which does differentiation. And to do differentiation, as we know, if we have a first order derivative, then at least it has to be a first one-time differentiable. And if we have kth order differential operator, then it needs to be a k times differentiable, which so-called the ck notation we have used. So whenever we have a differential operator, then kind of the natural space is not L2 always, as you can see here, right? I mean, if you have L2, then it's super, but it's not always you have this L2 structure. And this space, in general, I mean, unless you restrict something, is not a Hilbert space also. So we need to go beyond Hilbert space for some aspects, not for everything, because again, quantum mechanics, we need specific Hilbert space, but then there are other things which need to go a bit beyond, and then we will come to Hilbert space. Okay, but to come there, we need to, it's like a detour. If you want to go somewhere, then sometimes you cannot just go from A to B in a straight line, rather you have to take a detour. So let's talk about a bit of these spaces, yeah, that arises for differential operators naturally. And the reason is we want to define differential operator and discuss a lot about differential operators, because that's important in Schrödinger equation, that's important in some other applications in quantum mechanics. So the first space we are going to discuss, we have already seen this space before. This is the space of smooth functions. So I consider a non-empty open subset of RD U, and as I told, unless, okay, so we work with K, and U is of course non-empty open subset. I mean this, so my convention is that this can be equals to, okay, so I don't want to write always. Okay, Now, since all of you have this introductory or basics in real analysis, I hope you got some idea about neighborhood or at least convergence, right? So for real analysis, convergence is kind of, you have a natural choice that you just take absolute value of two number and then you say, okay, how they are approaching to each other and in which conditions, in which sense of limit, that thing. But for more general situation like this, you need to cook up something more. For instance, in the Hilbert space, we have a natural norm. Yeah, so we use that. Unfortunately, for this space, we don't have a natural norm. In fact, this is not a normed space also at all. So this is something more general. These are called topological vector space. Again, due to time constraint, I'm not going to detail, but let me try to give you very basics or very bare minimum. So what we want is the notion of convergence. How we can say something is converges in this space. And if I go like for real numbers, what we did for real number are we had absolute value, right? For a Hilbert space or even any normed vector space, we have norm. And now we do something is called a semi-norm. Again, I'm not going to define very formally what is a semi-norm. It has two properties of norm, but one property is not satisfied. That's what's called a semi-norm, which is not we'll see concretely. So let me just define it and then discuss it. So I will use this three parallel line, sorry, horizontal line. So 1, 2, 3, dot 3. And this will depend on two parameters, alpha and k. We'll see shortly what these are. So as a norm, as like any norm, this is a mapping from this space to numbers, real numbers. And how they are defined. So you take an element alpha k is defined by supremum. You have seen this thing before, over x in k, where k is compact subset of u, and we have used this multi-index notation before, right? D alpha u, and now this is a function of x. You take its absolute value. Okay, so that's the thing. So in other words, we can say that a sequence converges in this C-infinity space if and only if its derivative converges uniformly on compact sets, right? Because this is our K compact. So we can write that a sequence UN converges U in this space infinity U K if and only if all of its derivatives converges uniformly where uniformly on compact subsets of U. Okay, and once you have that, so now we endo so we have this smooth functions on U, and now we endo with this seminorm. And that defines a topology because we have a notion of convergence. And this space is sometimes denoted by E, U, K, due to the notation used by Lorentz Schwarz. Okay, and this is called a Frechet space. So named after French mathematician Frechet. Again, I'm not going to define all these things because it will kill too much time, and this is also not necessary. Just know that when you have this space, then you have a notion of convergence that is given by these seminorms. And once you have this structure, then this is something called Frechet space. So is it clear, or should I explain more, or you are completely lost? Okay. Thanks. So now we introduce, I mean, again, we talked about it, but derivative of the need to converge on all choice of. Yes. So you take this because you take supremum over all compact, or in other words, any compact. Okay. So there's the thing. Okay. Now let me introduce the notion of support of a function, which is the elements in U. So, I mean, now we are considering this such that U of x is non-zero. So in other words, you take zero, all non-zero, and then you take closure. Okay, that's the support. Now it may happen that the support is a compact subset, or all the supports of U remains in some compact subset. So then we have this space. So this is space of smooth sections, and now we put a C for compact, which means that U is a smooth function such that support of U is a compact subset of capital U. Okay. And now question is, can we use the same topology to talk about convergence? The answer is no. To define topology in this space, compactly supported smooth functions, is a bit more complicated because we need to take care about this thing which is not present here, right? So that's the additional thing, and we have to make sure that. And the way this is done is that, okay, you take subsets of your say ambient or the set you are working in this case U, such a way that this subspace is nested. And if you add all this, then you get the whole thing. So this is something called exhaustion. If you are not familiar, doesn't matter. I'm going to write it. So K1 is contained in K2, K2 is contained in K3, and dot, 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 dot. So these are compact exertions. And if you take union over all this case, then you get the whole thing. Okay? In other words, you are making small pieces of this guy, or you are say gluing pieces of this guy, but not in an arbitrary way, such a way that the first one is contained in the second one, second is contained in third one, and so on and so on. Okay? Okay, now what's the advantage or why we are doing it? So one thing is now clear. If we consider compactly supported smooth functions on any of these ki, then this is same thing here, but now is supported on ki, right? So this is same as before, but support of u is now ki. So in a way, we know it's compactly supported. Of course, this we know by definition, but we also know where. Okay. Now for each function u in compactly support, sorry, this looks like complex C. Compactly supported smooth function on u, there exists an index, let's put it k, such that for all I, so I is this I that we, or maybe I put k if n if you want. So this is this one dot here. Okay, greater equals to k, the function u has support in ki. Okay, in other words, you can think like, okay, we have this structure for this set, and we want to imitate something also for the functional space over it. So this is something called, or you can write this way, a directed system compactly supported over AI, and then compactly supported A2. Okay, so we kind of try to imitate, say, the set structure and the level of functional space. Okay, so now why we are doing this? So we are doing this so that if we define a topology here, then we can talk about topology kind of like this way. I mean, not really this way. Okay, let me show in which way. So remember, all these are subset of smooth functions, right? That's how the definition. Now, if we have a subset of something which has a topology, then what is a natural thing to do? You just consider relative topology, right? Consider that. Okay, so then consider relative topology. So those who are not familiar, you think about, okay, you have a topology on here. Let me write. So we have a topology here, and this is a subset. So you cook up a topology using topology from here so that all these open sets here are also open sets there. That's something called relative topology. Yeah. Okay. And then, since you have this structure, what you do, you use this directed system to define the topology on your whole there. So this is something called inductive limit topology. Again, I'm not going to write it because then I have to talk about what is an inductive limit. I'm not going there. Rather, let's try to imitate same thing. So how you define convergence? We say that this converges if all the derivative converges uniformly on all compact sets. And now same, but now just rephrasing a bit, maybe direct way. So all this, what it really means is that UN converges to U on compactly supported functions. This means that, okay, let me write here. UN that converges, sorry, write this way. Okay, that converges in this if there exists a compact set K, compact, such that remember I told you we have to control the support. So this is contained in, okay, I put Kn, and what we are converging? U. So support U is contained in K, and what condition should we expect? We are using relative topology. That means the topology here also show up here. And what is this? That all derivatives converges. So put it there. Derivatives UN converges uniformly in K. Okay, so yes, all the KIs are compact. All right, so is it clear what is this topology here? And as before, we now endo this with the so-called inductive limit topology, which means nothing but this. And following Lorentz Schwarz, we use this notation T. Okay. So is it now clear how we can topologize these two spaces? And this is more general than Hilbert space, but at least concretely you know how to check, right? So I give you time to think. There is a question that the Fisher space, Fisher space algebra, does it form a differentiable graded manifold? I mean, there is a topological property, right? Not in general. So there is something called Frechet manifold. These are like infinite. So, okay, uh, these are infinite dimensional spaces. So when you want to make manifold structure out of this stuff, then you have to talk about infinite dimensional manifold. And infinite dimensional manifold, if you just take a very basics, you just say that, okay, this is something which you can map to in a proper way to some Hilbert space, but then these are not Hilbert space. Then you say, okay, we relax this thing, and instead of Hilbert space, we map to some Frechet space, and then everything is matched nicely. Then it become a Frechet manifold, but at this setting, we don't have a manifold structure. We need a bit more, but yeah, we have a topology. All right. So I do understand it might be pretty abstract if you're seeing it for the first time. So please, please, please feel free to raise your voice, ask your questions, feel your discomfort. So feel free if you are feeling lost. I mean, you can at least write me on chat that I'm feeling lost. So there is nothing to ashame or feel uncomfortable, because I am really squeezing quite a different topic together, and I do understand due to background issue. I mean, I also suffered from this, and I still suffer. So please feel free to raise your voice.
What are the purpose that you define the restriction and extension?
You will see next lecture tomorrow, more concretely, because we are going to define self-adjoint operator. And to define a self-adjoint operator, we have to extend the domain sometimes, and then extending the domain related to the extension. And a restriction, we will see also for, I mean, it's like we have to change the domain sometimes. Sometimes we have to restrict, sometimes we have to extend. And that's the reason we defined it. Yeah, I haven't shown you any concrete example, but it's coming. So next two lecture we will go extensively about self-adjointness, and then you will. So we are going to play a lot with domains. So today I am introducing a number of spaces and topologies, and next we are going to use it to engineer the domain so that we can get what we want. And sometimes it's not possible also. And one thing, since it's related to quantum mechanics, you will see for some application we have to restrict also in quantum mechanics, and sometimes we have to extend. And that's actually related to this unbounded operator domain fact, mostly.
When we talk about the compactness, so why we need extension or
I
we
mean,
need the support concept?
you mean this one?
Yes.
Oh, this is not extension. This is exertion. Is H. So this is just what is mean that okay, you take compact subset of U and then such that you uh, take union and then you get the whole set. That is called exertion.
Ani, when we say something is compact, then how we can extend it?
Oh no, no, we are not extending here anything. So this is not extension. Uh, so maybe I write it. Sorry for my handwriting. So this is X H A U S C I O N, not extension. So here we are not extending anything. It's just we are taking. So if you have this two structure, then this is called okay. If you have a structure like this and this is called like you exhaust some set by something. And now we are not just exhausting by any set, rather we are exhausting by compact set so that we can keep this property. That's the reason we are putting compactness here. But here we are not extending anything. Is it clear now?
Yes.
Okay, thanks for your question. Any further question? Feel free to raise your discomfort. I do expect. Why did we start looking at compact supports from fresh air space? You will see. We will see why we have this fresh air space and all these things. You'll see within maybe 10-15 minutes. Okay, maybe I keep go to something more, say, why we are doing this. Okay, that's definitely the question. So please bear with me for two more definition and then we will see something interesting and something that I believe most of you are familiar with. Okay, so now we define something called a distribution. So in one sentence, a distribution is topological dual of any of these or some other sets. Okay, so definition, linear. So I will always talk about linear, functional, U on compactly supported function U on K means that U takes an element of this space and gives a number. So I put phi and then U of phi. Okay. And it's a linear. That means if you put some number, then you can just add. So the usual thing about linearity. Okay. So a functional on this is called a distribution. Sorry, I want to write a bit different way. sorry. Let me rephrase a bit. Let me first write and then I shall explain to you. So by a distribution, I mean a continuous linear functional on this. You can also consider the other space we have, the space of smooth functions. Okay, I'm not writing the because that part is same. Now question is, what is a linear functional and what is mean by continuity? So by this, by a linear functional, we mean this mapping. Okay, so that's the linearity. And now we have to talk about continuity. So this is linear and this is continuous if, sorry, so U acts on or test. So, okay, element of compactly supported functions are also called test functions. Test functions. And then we take their absolute value. This is called continuous. So you know the notion of continuity, that this can be approximated by something in terms of this guy. So some constant, and then sum over. So since it's continuity, you, I think, expect something with differentiability, right? Because that's how continuity comes. And now you say, okay, where this depends on x. So we play the old game. You take supremum. Okay, maybe I should write it. So d alpha phi x k as before. And now we have alpha. How far we go? We say, okay, alpha less than, okay, now I am, so this is a small k. I should write very carefully now. So alpha is less than or equals to small k, and here x belongs to compact k as before. Okay, so if this is true, then this is called continuous. Instead of compactly supported, you can also take smooth functions. Still this holds. Okay, so now you know linearity, you know continuity. And when you have both, then you have a distribution, and this is called topological dual. Why topological? Because there is something called algebraic dual that we will discuss maybe a bit later part of this course. But right now, by dual we mean topological dual. Okay, and then there is a notation. So compactly supported. This is the prime. And that's usually, okay, so that's called the topological dual. It's called dual of compactly supported functions on U. And as before, you can also consider smooth. Then you put this. Okay. Now you may wonder, okay, this space has topology, both of this space. How about this? Yes, you can also define topology of these spaces. And then we use a bit different notation. So now we use D dash U. Okay. That means we have the topological dual of this space and the topology. Oh, sorry. And same, instead of D dash, you can consider E dash if you consider smooth functions. The topology I am not going to talk right now, but it's not hard. You will see at some point. But topology means there is a notion of convergence, right? Okay, so that's we have our distribution. So now back to question, why we considered this thing. So one thing is this at again. Okay, if we consider this thing, then you have these two sort of distributions. Now question, can any of you give an example of a distribution? Think about this notation. You have seen something which has this property before. And that's immensely important in quantum mechanics also. So hint, who knows quantum mechanics. That's precisely. That's precisely. So Dirac delta. So Dirac delta is not a function. This is a distribution. And let's see how it satisfies this property. So the first one. So example, our favorite example. So now we consider just R for simplicity. So whole R. And let me recall the definition of Dirac delta. So Dirac delta compactly supported on R to K. Okay, sorry. Since I am writing properly, why not to write properly? Dirac delta. This maps compactly supported on U. So U can be R, okay? And maps to K. And then you take a test function, and Dirac delta gives you, sorry, E of 0. So first of all, is this definition known to all of you, or is this definition comfortable to all of you? The reason I'm asking this, because sometimes in physics literature, they have a different definition, which is not a definition at all. And in some sense, this is wrong. But let's go there later. So is this definition, who is not comfortable or who is not familiar with this definition? Okay, maybe I should go for a poll because that's really crucial. So, and we haven't gone for any poll. Maybe we all are exhausted today. So, all right. Please have your voice. So, distribution is something that often is completely ignored in physics literature because large part of physics literature pretends as if distributions and functions are same, and we will not go in great detail because this is not a course on distribution theory, but they are no way same, and Dirac delta is fortunate or unfortunately a burning example which is not a function, yet a large number of physicists think this is a function. Okay, at least 60% of us, we are alive, not sufficiently bored by this lecture. So let me end it and share this result. So around 70% of us, we are not familiar with this definition. So, okay, usually we see this, which is wrong as far as we know, but taking an integral on both sides leaves f0. So here Dirac e. Okay, let's see. Let's see. We go there. So who is familiar with this definition? I mean, you can raise your voice or you can write chat. Yes. Okay. Now, okay. I mean, you. I hope it's understandable, but in case not, let me write it. So you can also write delta A, and then instead of 0, you will get A. Okay. Now, that means this side equals to this side. So this side should equals to this, right? So let's do a simple thing. So this and this tells us integration of Dirac delta phi of x dx is same as Dirac delta A of phi. Right? That's the logical thing. And now comes the thing that you can integrate something if it is integrable, right? We have talked about L1, like L1 is the integrable functions. So if something is not integrable, then you cannot integrate, right? If it is not, it's not. You cannot make it integrable by doing something. Now, this guy is not L1. It is not even a function at all. Why? because there is no function. Okay, so there is also, say, u or r, whatever you want to write here. So there is no function which has this property. Sorry, this property. So I believe you have seen this expression also, that integration dx equals to 1, right? Who are you familiar also with this property or this way of writing? Yes. So now find a function which has this and this property. You may also see in this sort of thing like this equals to 1 if x equals to a, and it's not equals to, then it goes to infinity, right? So then you have this sort of mental picture, like Dirac delta is something like this. So this is the width, and as you go closer and closer, then what you do, you make the width thinner, but you go it higher, but it's still so it's same, so that integration gives you 1, this sort of intuition, right? So now if you look at integration theory and you say, okay, I want to find a function which has all this property, then you will see there does not any function with this property. However, this is true in this sense. In other words, you cannot write this as the integration of this, but this is true. And that's the reason, I would say. I mean, there are other reasons, but that is one of the reasons you need a more general object than functions. And Dirac delta is an example. And that's why we need distribution. And quantum mechanics, we need Dirac delta, we need, therefore, distribution. And now come back to question. To define distribution, we need this Fréchet space with compact supports, because Dirac delta is a distribution which takes test function as its argument. So now hopefully you see your questions, at least why we have done it. There was another question. You write usually this, which is wrong as far as I know. No, that is not wrong. That is not wrong. You can see from here. So, okay, I haven't discussed this. How you define a product between a function and a distribution. But let me write it. So this is defined by this way. Okay, so if U is a distribution, then the function times distribution is a distribution, and then you smear with the test function, that's kept like this. Now I apply this to Dirac delta. So f of x delta 0 x, and then you will put, sorry, you should not write x, phi. No, I want to write it a bit fancy way so that it's clear to you. This way. Yeah. Now we just apply it. Dirac delta f of phi. That means f of 0, phi of 0, which is f of 0 Dirac phi. Okay, so this is correct when you use the correct definition, but not in this sense. So is it clear to every one of you that there isn't a function which satisfies this property, as I just told verbally, or do you want to see the proof? Or I mean, okay, maybe I give you the floor. So questions, what you your discomfort, your comfort, your any comments, questions, comments. Because this is one of the really thing why you need to understand the difference between proper mathematical language and concepts and the heuristics, and why the heuristics breaks down. This is one of those cases. So is it clear that is the distribution? Is that clear? For instance, one of you have written, I do not know how you satisfy this definition. Now you can see. So this is your definition. So you have your definition. Now you take this guy. So this guy will be nothing but only this. Okay, let's check it. Let's write it. I need a bit of space. Make some space. Mhm. So that means I'm just taking 0 because it's changed nothing. This equals to phi of 0, and now matches with this. Can you match? Because now alpha equals to 0, there is no derivative term. Phi is 0. I mean, there is no supremum because this is just equals to, and since alpha is not to 0, this is not gone. And the constant is 1. Okay, so Dirac delta is a distribution as far as this definition is concerned. So is it clear to everyone? Dirac delta is a distribution in terms of this definition? Yes, no? Okay, at least clear to 1. Maybe, okay, 2. Only 2. Okay, at least we got 3. But we have 17. So only 3 people, for them you are clear, but not for others. Okay, maybe we all are tired. But please raise your voice. Feel free to express your discomfort. Okay, so distribution, I hope is clear. If not, you can ask anytime. But at least it is written here. Okay. I also make. Okay. Next question. Why this is not right? So who can say or explain to us why this is not right? For instance, one of you wrote that this is wrong as far as I know. Could you please share your opinion or viewpoint why you knew or you thought this is not right? You can write to chat or just raise your voice.
Because the integration is not defined at 0.
Yeah, close. But yeah, that's, I mean, not only is defined at 0, is not integrable at all. Okay.
Yes, that's what I meant.
Okay, good. Any other viewpoint? Or those who know this is correct, since we cannot have a function that goes to infinity at 0 and a 0, so the multiplication is meaningless. Yes, If you consider as a function, then of course and that's why this is meaningful, because this is not a function. You're right. So that's meaningful as a distribution, not as a function. Integration is not a limit. In which sense you want to tell integration is not? You mean if you are considering Riemann integral as a discrete sum and taking limit, you are talking about that limit or something else? Or you are talking about limiting procedure? Sometimes people try to convey this one. I haven't understood actually which one. Okay, last one. Yeah. Yeah, exactly. I mean, this limit is not really with that thing. That's also true. So it's just a very heuristic thing, which if you just think a bit carefully, then you see it doesn't make any sense. Okay, and yeah, any other who are not really comfortable that this is not right because you have seen various book, very famous book, any book, very famous scientist, physicist, everyone is writing, so why it is not correct? Feel free to raise your discomfort. That's what we are here. We want to talk about this. Okay, so it seems at least you got some idea, but please raise your voice. You can also discuss in this Slack platform, but I prefer as much as we talk here rather than there. But anyway, it's better than not talking. So let me then go further. Why we introduces this space? I hope you get one instant, and I hope you also get another example where this precise mathematical understanding helps in quantum mechanics. Those who doesn't know, take as a black box, Dirac delta arises in various instances in quantum mechanics. And unless you really know what is a Dirac delta and you use this sort of heuristic thing, you might be able to prove various things, but this doesn't make sense. Okay, I'm really happy. I'm really happy that it cleared some of confusion. So what confusion left? Feel free. You left some confusion. So what left? Please share with us.
The integration over the whole thing equals to 1.
Mm-hmm.
Can you get that from this definition, or it's just something?
No, this is not integrable. So it doesn't. This part doesn't make any sense.
Yeah, okay.
It's just not.
It makes more sense from the distribution definition.
Yeah. So this is. I mean, so people adopted this viewpoint because if you read, for instance, Dirac's quantum mechanics book, so he always wrote that whenever you have this guy, you have to think in terms of distributions. So always, sorry, inside integration sign. So he wrote like this entity doesn't make sense without being inside of a integration. And Dirac has very right intuition, but sometimes intuition is not sufficient even for a genius like Dirac. So let me give you a simple example how these things comes and why you really need this proper knowledge here. So let u is a smooth function and phi is a compactly supported smooth function. Okay. Now This thing makes sense. Yeah, you can just multiply functions pointwise. And this is again a compactly supported smooth function. Okay, now think this. So you integrate over u, you write u of x, u of x dx. Since this is compactly supported, so this integration makes sense, or it is integrable, or L1. Now you are familiar with these functional spaces. And let me write this just as a symbolic sense. U phi. Yeah, it's just a symbol. So this is what it is. Okay. Now you say, okay, instead of this, how about we consider Dirac delta? Then we have this guy, right? And this is phase 0. So the intuition Dirac had, probably, I haven't talked to Dirac, of course, is that you view this as some sort of generalization of this blue guy. Because you see, now you can consider blue guy also as a distribution, right? So you consider, let us consider it as a distribution. So I say like this. So U more space. Now I define this by this. Is it clear now that U is also a distribution? Okay, so then, and you can just check. You satisfy these two properties. This property, one property is already. Yeah. Okay, so that means U is a distribution. But this is a very specific type of distribution which can be written in terms of integration. And this has a name. This is called regular distribution. In other words, any smooth function can be viewed as a distribution. But in which distribution? A regular distribution. Okay, so very important, this word I want to highlight. So any smooth function can be viewed as a regular distribution. So Dirac almost discovered distribution theory. So he was here actually. he got up to this point. So he thought for Dirac delta, now if I write is, no, I want to use red as a caution. So he thought this equals to u x dx dx equals to phi 0. Yeah, because you write this as delta x minus 0, and that's okay. That's what he is. So he was really very close to discovering general distributions, but this is not correct. This is correct, but not this, because this cannot be written in terms of a regular distribution. So that's really the distinguishing property. So Dirac was, again, I'm not taking anything. Even if I try, I cannot take anything from Dirac. He's just, and his level is so where. But I just want to give you that, I mean, it's super important, or it played a super pivotal role. But still, you see that to get from intuition to the proper mathematical object, sometimes you need to push one step further. I mean, maybe if Dirac tried, he could also get it, but he just stopped here. And that's how, in physics community, this misconception arose. So people used to think, oh, since this is a regular distribution, so this also makes sense. We just say that, okay, this is not exactly u of x, but this is something like u of x, okay? And now how we can make something like u of x? How we can make something like? And then you want to do back calculation. How can we make it working? And then you come up with all these things, which intuitively not bad, but if you really put in a proper mathematical setting, doesn't work. And it makes a lot of confusion, as some of you express. And when I was a master's student, I also got so much confused. Some book like this and some like this, and then so in undergrad I studied engineering. In engineering, you also get a lot of Dirac delta, and this is a very widely used intuition given. So you consider in terms of signal. A signal is like this, and then with time, signal spreads. But initially, signal was very high, that sort of thing. Intuitively, again, it makes sense to me, but once I tried to learn some integration theory, then I realized that these are words. If you really put in proper framework, this doesn't work. Again, this is at least unfortunate from my viewpoint, but physicists, or most physicists, don't think so. So they still want to view this as some sort of object like this. And that's why they keep writing this way. And of course in engineering. But maybe we can do an homework about this, that prove that Dirac delta is not a regular distribution. Okay. So is it now clear, especially people from more theoretical physics background, why you see this sort of expression? And then, yeah, now again, what's question? What makes you confused? Or if you have any confusion about Dirac delta, whatever.
No more questions, I think.
All right, so no questions, no comments. Is everything clear about Dirac delta? I hope after this, you will never feel confused about all this fuzzy, intuitive idea that sometimes makes sense but not really works out end of the day.
I see the Dirac delta when it's come in the equation, it make the equation easier. So it is.
Yes, and we will also encounter some of this. It makes equals definitely easier because of this property, right? This is the property. All right, so now let me keep going. So now we have distribution. Are there other irregular distributions in quantum mechanics beside Dirac delta? Let me think. There are, for instance, if you consider hydrogen atom, okay? So hydrogen atom, you have potential like this. One by, I forgot the power. So let's put x to the power n. Then you can prove for some value of n, this is a regular distribution. But when you go to x equals to 0 or x tends to 0, depending on the situation, then you see that this is no more a regular distribution. So this is, in other words, regular distributions are those which are integrable. So this is not always integrable depending on your dimension. So depending on n, maybe I write it in n, depending on n and the dimension we are working, this is not always integrable. And you see Coulomb potential or hydrogen atom in quantum mechanics. We shall not have time for Coulomb, but that's also a very interesting model on quantum mechanics where spectral theory has really to offer beautiful results. All right, so then we have 5 minutes. Let me introduce a thing shortly. So integration by parts idea, if we think, so now in the same footing as here, okay, we are using same footing. So u is a smooth function, and we are doing integration by parts. Then you know, if you do integration by parts, you will get a minus u d phi dx phi, right? That's the integration by parts. Now for a general distribution, how you go? So definition. So let me just write partial I. X or I doesn't matter. So this acts on smooth, at least continuous, but now we are talking about smooth functions. Okay, since we have u, let's keep u. To itself. And now back to, some of you ask why we need restriction. We will see shortly. So if there's the usual thing, then we define I put a prime I, which means that this is acting on the distribution for that. How? Distribution u to k, and how you act. So you take an element of this distribution u, map by du. This is again a distribution, and then you smear with a test function. How? You just try to imitate, because you know for the regular distribution this is true. Now maybe like Dirac idea or I don't know whose idea. we just use this also for regular general distributions. So U. Okay. Now you say, okay, why we are only considering smooth functions? Let's consider restriction. Yeah, we define restriction. So put C, and then still it well defined. You just go on with restriction. Okay. So this guy is called distributional derivative. And as you see, a distributional derivative differs from usual derivative only with a minus sign. Sometimes distributional derivative and usual derivative doesn't also differ with a minus sign. For instance, if you put some I with a sesquilinear form, then sometimes that change. But you have to keep sure that this operator and this operator are not same. Because, yeah? Why they are not same? Can anyone tell us? Exactly. Domain. They act on different domain. And now you see why we talked so much, we stressed so much about domain, domain, domain. So we will see shortly, this is also an unbounded operator, and this domain is different from this domain. So even there is a plus or minus, the domain is different. So they are really different object. So we are over time, but let me just use 1 minute because. So now we just imitate this for a general situation. So we have a operator. So it's a differential operator, L, on smooth to itself, which means that take phi and then L of phi. Given that we define its distributional derivative, sometimes it's also called dual. Let me give by L prime in the distributional space to itself. So U maps to L prime U, and then we smeared with a test function. And then we call this is nothing but U L phi. Okay, it's just same definition we act. Now, in practice, sometimes we omit this notation. We just call it acts distributionally, okay, without writing a different notation. And then you will see same L, notationally same L here and there, but they are not same L. It's just written in text, just for simplicity and not to make your notation very cumbersome. Okay. So that's called, so maybe I write a differential operator in distributional sense. Okay. And when distributional operator acts in this sense, this is something called weak sense, or it is called weak derivative. In other words, weak derivative for regular distribution is same as distributional derivative on distributions. Sometimes people also use this word interchangeably. Okay. So once you know, I think it's clear what is meant, but unless you know, then it's really confusing. All right, so we are slightly over time. I'm sorry for that, but maybe I give you a few minutes. Any questions, comments? So I keep open for 5 more minutes if you have questions. Okay, so for those which is very abstract, I do understand, and I also feel like you when I started. So one way to do some homeworks, or I would say more than the given homeworks, and especially do in an honest way. You know, we are in the era of ChatGPT, Claude, all the AI models, and I have not even tried to cook up anything which AI cannot solve. I am giving very standard homework because I want you to learn standard thing, and then once you know this, you can go for advanced thing. But to get used to, or to get comfortable, or to understand, please, please, please try homework on your own. So the trying is not only to solve, because you know it's not a professional exam that you get pass or fail. It's like a learning process. And I don't know how the learning process will be in future, but as far as current situation, I would still say it's an evolutionary process. So when you keep working with something, spending time thinking about it, then you get real understanding and real feeling. Another thing is to look at examples. So, I mean, since, of course, I hope you understand, I have a time constraint, so I cannot give a large number of examples, but look for examples. Ask your favorite AI apps, give me example, explain this or that. Look at the references of the books I have given you. If you don't like this, there are other very good books. Look at those. You can find more examples. And again, do not only just look. There is a difference between reading and understanding, right? And understanding means you look at example, you try to do it, you cannot do it, and you see why I cannot do it. Oh, okay, this is why I stuck, and you try to do it. It may take a long time to do one example, but this one example will give you understanding, because this is not about getting marks, this is about understanding. So number two is examples. And number three, just ask. Like, feel free to ask. I am lost. It's perfectly okay. And that's why I am here. I am not talking about anything that is not available. Any standard reference is everywhere. So why you are spending 2 hours of your life with me? The only reason I would say, to give you this freedom, ask, say, I am lost. What should I do? So in this sense, I would say, like, take a small step. If you are new, take a small step. For instance, if you are new to distribution, okay, just take distribution for instance, and then you take this definition, okay, very abstract definition. Then I have given you one example, you do it on your own, maybe it's very simple, and then you look some other example, for instance this one, or you open a book or lecture note or AI app, look for other example, try to do it, and then relate what you know. For instance, I haven't given you the proof. Maybe this is a nice thing, like, try to prove why there exists, why there doesn't exist any function with this property. If you cannot prove, I also couldn't prove when I started, because I didn't know about integration theory, I didn't know about reanalysis. And then I started to learn about how to do integration, what is the integration theory, and it took a long time. But again, we are not in a race, right? You are not in a race. So take your time, learn small things slowly, but learn properly. You don't need to overwhelm by all of this. Oh, I have to learn everything and I have to know everything. No. If you can learn only one thing from the whole course, I would say this is better than knowing 100 buzzwords without understanding anything. Especially in this era when AI knows most of the stuff. And after doing all of three, if you still feel lost, feel free. Let me know. I shall then think about something else or try to do it in a different way. And you can also tell me, if you do this way, if you give this example, if you talk about this, then this is easier for us to understand. You can write me personal message here or the group. Yes, so that I shall also try to incorporate that. So does it gives you some positive way of approaching for those who are feeling lost? Yeah, take a small step. You don't need to do everything, and I know you have your regular study, and that's most important thing. But as I told, at least try to learn one thing that you can say, okay, I learned something after spending 2 hours. Why you are spending your 2 hours if you are not getting something from here? Yeah, any other questions, comments?
When we see the manifold language, everything is geometrical, but here the imagination is very difficult to imagine the mathematics.
It's true, because many, as you told, when you have geometry, then it's easier to visualize. Unfortunately, functional analysis is not always geometric. But there are application of functional analysis in geometry, and the other way around also. Unfortunately, we will not have time to go these geometric applications, but some of functional analysis is highly used in geometric application, like wave equation in a manifold. You use functional analytic technique. If you want to do quantum field theory in curved space-time, then you use functional analytic technique in geometric application. If you work on general relativity, you sometimes use functional analytic technique for geometry. And sometimes the other way around also. Yes, someone wrote, "We don't understand things in." Yeah, that's a famous quotation by von Neumann. And I think now you can relate. Much of these things are, okay, not distribution theory. Distribution theory is originally due to Schwarz or even Sobolev. But unbounded operator, what is the main topic of our course, is developed mostly by von Neumann. And you can also get motivated from his comment. But concerning your comment, that's true, but also at some point you will see some intuition. For instance, I hope this gives you an intuition, like how inner product space is related to geometry, like it's a notion of angle, and then Hilbert space is a higher abstraction, but still you have a notion of angle in an infinite dimensional space. And yeah, today we discussed actually very abstract and mostly concepts. So here I don't see much geometry. Also, yeah, tomorrow will be also very analytic. So tomorrow we'll go to the self-adjointness. But you will see, I would say, impact of geometry. Okay, impact of geometry in self-adjointness. Like for instance, if you have a boundary, then how it changes the domain of an operator. You see this sort of thing. So you will see the interplay also the other way around. But I do agree, mostly that's people like geometry. So geometry always has a nice thing. On the other hand, functional analysis often is abstract and not very thing. I do agree with you. Okay, there is a question. Is a regular distribution analogous to Haar measure? Um, Not always. So for Haar measure, you need a group action and some compactness, and then you can define Haar measure. But for regular distribution, you don't need group or anything. So in that way, they are not related. But regarding measure, uh, maybe that's what you are looking at. Every positive distribution is a measure. Okay, and then if you consider a group action on a distribution and still it is a positive, then probably there is a relation Probably I expect, because it's the general result that every positive distribution is a measure, and then if you put this compactness and group action, then I think people have worked it out that when you can look at Haar measure from distributional viewpoint. But in general, distributions are way general. But there is a very direct connection with measure. And those measures are more general than Haar measure. So as a special case, I expect something, but I can't pull any concrete statement right now. But again, you need positivity, yeah. Otherwise, it's not going to work. And that's, I would say, probably another reason why quantum mechanics and quantum field theory is so hard to understand, because it's not a geometric theory. On the other hand, general relativity, I mean, depending on, but I think most people will say that it's easier to visualize because it's very geometric. So
yeah, if something is infinite dimensional, then we can do everything we want.
yeah, exactly. Whenever comes infinity, then life become horrible. Whether you have infinity in number theory or set theory, or and unfortunately, yes, quantum field theory is another issue. And in fact, so I asked this question to my second master supervisor, that how much math one should learn to understand basic quantum field theory. And then he replied me roughly speaking like that. Uh, if you really want to understand what is a quantum field theory in a mathematical way, then no one knows the answer, because we do not know what is a quantum field theory still. So we do not know. Even it may happen, the language required to describe quantum field theory has not been discovered yet. For instance, like this, unbounded operator was not discovered when Heisenberg worked it out. So Heisenberg did it heuristically and this and that, and then people like von Neumann, he did this thing. So in a way, for quantum field theory, the problem is even more complicated than this, and we do not know the proper mathematics yet. And this can be another reason why we do not know what is quantum field theory. So this is one viewpoint. Not everyone agrees with this. So if we know the proper description of quantum field theory in a mathematical term, then probably we can do much better or more general situation.
If we can apply it on real problems, then we can understand the
Well,
quantum.
we can apply real problems, but we can do, say, more real problem. For instance, I mean, quantum field theory is a huge success in terms of a standard model. But if you include gravity, for instance, classical gravity, not quantum, then it becomes very complicated. And of course, quantum gravity is an unsolved issue for last 45 years. So some people think the reason is that we do not know actually quantum field theory, even in Minkowski, in a proper way. And that lack of understanding is the reason we couldn't solve the quantum gravity or semi-classical gravity properly. I mean, I have inclination towards that, but I don't want to impose of any of you. Okay, so someone asked, while conducting the course, could you please relate this course to monoidal category, since I think the course will build a foundational concept tensor category set. Unfortunately, neither I have time, because you see, I have only 16 lecture. And even to introduce category theory, I need something. That's, I would say, more fundamental reason. And second, I would say, I mean, you can describe quantization as a functor, and that's a very beautiful way to understand it. But yeah, I would say it's mostly lack of time. Yeah, because if I have to go in the category theoretical description, then I have to introduce, right? I cannot just say, okay, quantization is a functor between this category and that category. yeah, I have to define what category is that. And yeah, had I have more time, I would love to go in also that direction. That's another beautiful, it's a global way to view quantization. But yeah, I'm really sorry. I think I shall not manage time. A talk. Again, I mean, even 16 lecture is not sufficient, or even forget about sufficient. I'm not sure even 16 lecture can we do anything reasonable. So, but I'm really happy that you are interested, and if some other people are also interested. But question is that which time? I mean, timing, I would say, is the issue, right? I mean, maybe I would say so there are research talk in this ICTP. I would say maybe that's the nice point. If how about that? Maybe we can propose the organizers to give a accommodated talk from categorical viewpoint. But concerning the other part, the fundamental concept of tensor categories, yes, we will not go much in tensor or entanglement sort of thing again for timing. Otherwise, I would be more than happy for that. So you are right. If you keep going, you can go in that direction. But unfortunately, due to time constraint, uh, we shall be go very little. Yeah, I mean, as I look, I mean, my plan is to do harmonic oscillator, which is actually beginning of quantum mechanics. And even harmonic oscillator, we shall not be able to do everything. Even as you see in distribution theory, I'm just talking about bare minimum. There are so many things which should. So I do appreciate your comment, and I will convey this to the organizers. You can also write to the organizers. Maybe there is a talk. We can arrange a talk about it. Yeah, you're welcome. And also, we can talk during or after lecture, say more informally. There is no problem. And yeah, it will be also nice if some of you share your viewpoint about quantum physics, what you think. If you have idea, maybe after lecture 10 minutes we can talk about it. Yeah, it has not to be mathematical, I must admit. Just feel free, like you think like this way, because there is also issue of foundation of quantum mechanics that we are not going to touch at all, and part of that is also related with mathematical foundation. Okay, and that people are also working on that. So there are lots of interesting things. So there is a comment. Yes, so there is an algebraic approach of quantum mechanics and quantum field theory, and that is also super interesting. Again, that is something I will be more than happy to talk. In fact, I work on algebraic approach in quantum field theory, so that perhaps even more than this thing. I mean, not more, but I love to talk about that because that's my one of area of research. But then you really need a separate course if you want to talk about algebraic approach in quantum mechanics. But I must admit, tell that this will be also useful there. So if you know at least a functional analytic description of quantum mechanics, then going to algebraic approach is much easier because this is also useful there. It's not like this is completely isolated. And also, who loves geometry, for instance, general relativity, some of these things, not exactly, but some parts also arrow. So if you work on Einstein equation, solution of Einstein equation, then still it's a hyperbolic problem. And then functional analytic technique is useful, and then still it's not that intuitive, I would say, anymore. So if you look at some of the greatest result in general relativity, like Well-Post-Cauchy problem by Schokke-Brucha, um, it's an outstanding result, great proof, but it's a mixture between analysis and geometry. Yeah. So I would say also from geometric viewpoint, I mean, what you are learning is a very basics and you can apply in many places. For instance, I am right now working on geometry and I use quite a bit of functional analytic technique for solving some geometric problem. So this will be also useful for geometric problems. Because end of the day, we are not completely isolated islands. So yeah, I shall convey the thing that maybe we can organize some informal talk, or even there will be, there has every year formal research talk. So I shall convey the organizers to arrange one speaker from maybe foundation of quantum mechanics, category theory, or this sort of area. And if any of you has other wishes you want to hear, you can let me know or let the organizers know. We shall try at least. So are there further comments, questions? All right. If not, then maybe it's time to wrap up. Thank you, everyone, for your patience in this very abstract nonsense. But if you are not enjoying, please let me know. Okay. If you are not enjoying, this is my responsibility that I cannot present things in a nice way. It's not your fault at all. Okay. So please let me know that you are not enjoying. I shall try my level best. Then I don't see any particular question or comment. So then let me